Right, so welcome everybody. This is the first session of OOPSLA. We have a very exciting program. We start with an award-winning paper. So the first talk is by Michael James. He is talking about grounded Copilot, how programmers use code-generating models. Stage is yours.
Thank you. Hi everyone, I'm Michael. I'm excited to tell you about some work that my co-author Shraddha and I have done. So we are entering a new era of programming with tools like Github Copilot, Meta's Llama, and AWS Code Whisperer going to change the way that people program. If you're unfamiliar with these tools, something like Copilot offers quick completion of a program given just a prompt, any kind of prompt, be that a comment, a function definition, and it can complete the function or end of line for you. But as these tools are gaining popularity, there are important questions that we should ask about these tools to make them better. How do programmers use them? How do programmers tend to express intent? And what do programmers use them for? To answer these questions, in our paper, we studied and interviewed 20 programmers as they used Copilot. We identified patterns in the behaviors that they had as they used this tool, and we created a theory of those patterns. In short, our theory is essentially of programming fast and slow. Programmers are either in a mode that we call acceleration, which is kind of like a supercharged autocomplete, or they're in a mode called exploration, which is like a Stack Overflow plus. In this talk, I'm going to tell you about the method that we use to arrive at this theory. I'm going to give you more detail about our two modes, acceleration and exploration. We'll compare and contrast them. And I'm going to offer recommendations for future tools and other research questions to answer as a result of this work. So over the course of our study, our participants completed up to four tasks. Ranging from working in an existing code base to working from fresh code. We had a range of different challenges, from implementing business logic in a chat API to a networking task that few of our participants knew how to use, including using a custom crypto API that we knew Copilot would have no clue how to use. We had participants work across two different languages in one task, and another was a programming competition task that was easy to test. Among our 20 participants, we had about 15 from academia, 5 in industry, ranging in their language proficiency for their languages of choice, occasional, regular, professional users, and about half of them had used Copilot before. Now, how do you generate a theory from watching programmers use Copilot? To do this, we started with a broad question and two tasks. We had our participants perform these programming tasks. We interviewed them about their experience, and we recorded these videos. We recorded their sessions. We annotated those videos with tags that we created about what they did, how they got a suggestion from Copilot, what they got from Copilot, and then what they did with that suggestion from Copilot. We identified common things to find patterns, and we began to find a work-in-progress theory. We continued this cycle of developing new tasks to challenge untested parts of our theory, continued to annotate videos, and rework our theory as new data came in. We kept doing this cycle until we reached, in the grounded theory parlance, what's called theoretical saturation. That is, at the end of our 20th participant, no new data surprised us. And at this point, we could say that we had found a theory of acceleration and exploration. Acceleration, in brief, essentially is the programmer driving. It's kind of an autocomplete plus. The programmer has a plan, and Copilot helps them execute faster. Really, the programmer feels in the zone. I've got a little video that is emblematic of acceleration.
Oh no, this is values. Username equals text. Oh no, this is values. Send. Oh, there you go. Username already taken. Username equals text. Then, oh, there you go. Username already taken.
Okay, so this participant had a clear idea of what they wanted to write, and Copilot just completed the line and put the return for them. There was no thought about like whether it was right or wrong. It was exactly what this participant meant to write. So they just accepted it and were able to continue on. On the other hand, exploration is more about Copilot driving the coding session. Participants tended to treat it like a Stack Overflow++. Commonly, when the programmer is lost, Copilot could suggest solutions to help them get started. I've got another video here, another emblematic video.
Where I say,
this participant had no clue what they how to start this task, and they just they knew where to start, but not how to get going. And they left it up to Copilot.
Actually, look at that. Try, sure. Wow. I wonder if this is from not handshake. I like that solution or something. Okay, this seems potentially wrong, but I'll keep. Okay, not handshake. I like that. Sure. Okay. Great. This seems potentially wrong, but I'll keep. Wow, I'm such a good coder. Sure. Great. Wow, I'm such a good coder.
For this participant, Copilot helped them get started on the task and provided jumping off points to complete the rest of this chat server task. All right, so that was the two modes on a high level, but now I want to compare and contrast 4 different features of them. There are more in the paper, and I encourage you to check it out. So we're going to talk about the conditions that lead to participants entering each of these modes, how they prompt the model in these 2 different modes, what their edit tolerance is like for suggestions from the model, and how they validate that the suggestion meets their intent. In acceleration, if the programmer is able to break down the task, then we saw that they were much more likely to be in acceleration. They had a better idea of what they wanted for each subcomponent, and Copilot could offer a completion. Meanwhile, in exploration, particularly when faced with unfamiliar APIs or unexpected behavior, the programmer wasn't sure how to proceed, and Copilot offered a great place to get started. So, acceleration is great for small tasks, exploration when programmers are faced with uncertainty. For the prompting behavior, in acceleration, the prompting was largely unintentional. They had simply paused while they were typing, committing thought to code. Copilot saw that as an opportunity to present an end-of-line completion, and the participant could quickly see whether that matched what they intended to write, accept it, and move on. This was not the case with exploration. We saw programmers spend much more time writing comments, and they were willing to rewrite comments in exploration to elicit better responses from Copilot. Copilot would then often suggest multiple lines for these participants. So in acceleration, the prompting is often unintentional, whereas in exploration, they're comment-driven. Now, when Copilot gives many responses or multiple lines, we often saw participants in exploration mode cherry-pick parts of those snippets. They were willing to work with incomplete or incorrect suggestions because it still offered a good place to get started. Whereas in acceleration, participants really wanted a small edit distance from their expected piece of code. All right, so they were unwilling to edit in acceleration, and they wanted to cherry pick in exploration. Now, how did they check whether things actually match their expectation? In acceleration, we had this one participant put it really well for the specific things that they were looking for when deciding to consider a suggestion.
Maybe one way to say it, right, is I have a picture in mind, and that picture ranges from syntactic or textual features. Maybe one way to say it, right, is I have a picture in mind, and that picture ranges semantic about like the kind of methods that are being invoked, the order which they should be invoked, and so on. Like a literal and when I see a suggestion, the closer that suggestion is semantic about like the kind of methods that are being invoked, the order which they should be invoked, and so on. And when I see a suggestion, the closer that suggestion is to the mental image I hold in my head, the more likely I am to trust it.
So in acceleration, participants used a sort of mental pattern matching on the suggestions that they got from Copilot to decide whether to accept it and move on. That pattern matching was often on the shape of the code, the literal shape of the code, the set of method calls that were used, or what they perceived to be their own edit distance from a correct solution. Meanwhile, in exploration, we saw participants review the code carefully. When they got multiple suggestions from Copilot, they would use the frequency of how often, say, plt.hist appears to determine whether that was a valid suggestion or just a hallucination of the LLM. They would use frequency to gauge confidence of the model. They would run the code, and they would also check external documentation to double check the model's suggestions. All right, so we've compared and contrasted acceleration and exploration. We also ran a little bit of a small quantitative analysis of our results. We took the annotations and we analyzed them. And there are two interesting findings that I want to share with you. There are more in the paper. So we noticed that experts explored the least. They already had a good idea of the APIs that they needed to use or how to get started on a task, so they could spend much more time accelerating through their task. We also noticed that those who were new to using Copilot tended to explore a lot more. Those who had used Copilot before mentioned that they had reduced their trust in the model and they weren't willing to explore as much. Now, I have some recommendations for future tools and future research questions that we as a community could look into. In acceleration, we noticed participants often had this tension between reading a suggestion, the end of line completion, or just ignoring it and writing their own code. Oftentimes, participants were pretty good at maintaining a good balance, but sometimes it would go terribly wrong. Participants reported feeling sucked into reading a suggestion. They felt like, well, Copilot offered me this code, I should check that it was right. So I have a participant, I'm going to show you a video of a participant who was working on a programming competition task in Haskell, importantly.
I'm going to do, what do you want? I'm going to do, what do you want? That's interesting. Okay, hang on. So, see, I don't know why I was about to write the code. I was about to write the code and I knew what I wanted to write, but now I'm sitting here seeing. See, I don't know why I was about to write the code. Come up with something better than the person who's been writing Haskell. I knew what I wanted to write. But now I'm sitting here seeing if this somehow had come up with something better than the person who's been writing Haskell for 5. I don't. Why am I doing that? No, this is not what I want. Okay. Giving it the time of day. No, this is not what I want. Okay.
That Haskell code that Copilot suggested was so dense for this participant, but since it was just a one-line completion, he felt sucked into reading it and considering it. So we noticed that unexpected and complex suggestions tended to break our participants' sense of flow. So if a model could be more aware of the mode that a programmer is in, that is, if they're experiencing the effects of acceleration, then a model should be significantly more confident in the suggestion it provides, whereas if they're going slower, a participant might be more willing to look at longer pieces of code. There's also useful work to do in helping programmers validate suggestions. Like, could that Haskell code have been right? Maybe some small part of it could have been, By presenting intermediate values or intermediate types, we might help our users better and more quickly evaluate whether a suggestion fits their intent. We noticed that our subjects had trouble distinguishing suggestions. They would get multiple suggestions from Copilot, and then they would be left wondering, well, I know these are all textually distinct, but how are they really different? And participants would spend extra time considering the difference, playing spot the difference between many different suggestions. So there are some interesting research questions to help distinguish suggestions. In this space, particularly with novices who are trying to explore for the right approach to a problem, might be asking kinds of questions that the model could definitely help with. Like, what are different ways to solve this task? What are common API calls? And what are the edge cases to consider when implementing an algorithm? All right, so I've told you about how we arrived at our theory. I've told you about our theory of acceleration and exploration, and I've presented some recommendations for future tools and future research questions. I want to thank my co-authors, Shraddha Barke and Nadia Polikarpova. I want to thank my participants and you for coming to my talk. Thanks.
So we have time for 1 or 2 quick questions. Any question from the audience?
Really great talk, really great stuff. On your slide where you've got the 2 graphs where you correlated like professional versus not and versus previously using Copilot or not, was there a correlation between if professionals had used Copilot more than non-professionals? I was just wondering if there were...
We did not run that analysis, so I don't have anything to say on that.
Okay, thanks.
Any other questions?
Thanks for the talk. I'm using Copilot with Rust, and something that have been bugging me is that it's hallucinating in non-obvious way. Sometimes, you write something, and in acceleration mode, it looks like it's right because it has the right shape, but it uses a method that doesn't exist. And it's frustrating because if I were to write this code, I wouldn't do that because I use the LSP and I have autocomplete. And I wonder if you saw that as well, and if you have ideas about, I don't know, like making the agent talk with the LSP incrementally before showing the results, or some other external feedback loop before presenting it to the program.
What a wonderful suggestion. That sounds like a great opportunity to help, like one way to help validate the code that Copilot provides, to highlight, to say, well, I have an idea you could write it this way, but red squiggle, like this phantom text won't compile as is. Future work.
All right, so we need to move on to the next talk. Misha will be around to answer other questions after the talk, and thanks him again.